Professor Dave and Chegg here. We know that substances in the solid phase are characterized by particles that essentially do not move with respect to one another. They are locked in place. But there are many different types of solids that exhibit different bonding patterns and structures. Let's quickly list the types of solids we may encounter.
First, we have crystalline solids. These are solids that have some kind of reliable and repeating structure, and they can be categorized as molecular solids, network solids, ionic solids, and metallic solids. Molecular solids are just the solid phase for small molecules. So when water freezes to form ice, that's a molecular solid, because it's a bunch of tiny water molecules frozen in a particular lattice structure, which allows hydrogen bonding to occur. Each molecule retains its own identity and are connected strictly through intermolecular forces. Then with network solids, that would involve covalent bonding throughout the solid. So when carbon forms a diamond, that would be a network solid because covalent bonds connect every single carbon atom in the sample. Ionic solids involve ions that form a particular lattice so as to maximize electrostatic interaction between formally charged particles. This would be something like sodium chloride with positively charged sodium ions and negatively charged chloride ions in a grid. And metallic solids involve metals whose atoms form a network just like network solids, except that the metallic bonds that connect them are a little different from regular covalent bonds due to the way that electrons can delocalize and move freely through the system, allowing for the conduction of electricity. Molecular solids tend to have the lowest melting and boiling points, since the intermolecular forces holding the molecules together are relatively weak. Apart from these four types of crystalline solids, we can also have amorphous solids. These do not conform to an organized lattice structure, often because the molecules are very large and do not lend themselves to organization, such as with some polymers and gels. With the types of solids covered, we have a little bit more to discuss regarding ionic solids. Ionic solids can adopt a number of different unit cells, meaning particular geometries, depending on the identity of the cation and anion, as well as their relative abundance within the compound. Sometimes one of the ions is much larger than the other, and they can have different ratios, whether 1:1, 2:1, or 3:1, and this is all accounted for when the compound adopts the most efficient lattice structure possible. If a cubic cell, it could be a simple cubic cell. This involves a total of one atom per unit cell, given that we find an eighth of an atom at each corner of the unit cell. It could be a face-centered cubic cell. This involves 4 atoms per unit cell, given that we have the one atom chopped up into eighths at the corners, plus 3 other atoms that are each cut in half, occupying the 6 faces of the cell. And lastly, it could be a body-centered cubic cell. This involves 2 atoms per unit cell, the one atom chopped up at the corners again, and then a single intact atom right at the center of the cell. There are other categories as well, those being tetragonal, monoclinic, orthorhombic, rhombohedral, hexagonal, and triclinic. Again, the particular configuration adopted is simply the one that will maximize the electrostatic interaction between the ions and thus enable the system to get to the lowest energy possible. All of this information is typically collected through X-ray diffraction, where beams of light are scattered in such a way that reveals information about the spacing between the atoms of that substance. This is very sophisticated and is even used to learn about complex biomolecules like proteins and nucleic acids.
We should now be able to describe the different types of solids and offer examples of each, as well as understanding their properties. Professor Dave for Chegg. See you next time.